Yeah, so I had envisioned to talk about an overview of many projects we've been doing in Polytechnique around healthcare and data model. But following the first few days of the workshop, I felt that people really were craving for details and more depth. So I just kind of reduced that to what we've been doing around cancer treatment. And so I'll be going over a set of projects in that field. Just normal statistics, which are very sad, and the fact that cancer is affecting a lot of us. I bet everybody here knows people who's been affected. Hopefully they've made it, but we all suffered losses from that disease. And so it is not going to get better, unfortunately, with the aging of the population. And there's a crucial need to kind of being more efficient in servicing, treating, and managing those cases. So for those of you who've not really delved too much into cancer treatment, our ability to fight this disease comes in three main ways. First, if you catch the disease early enough, you can remove the tumor by surgery. And this can be done in conjunction or disjunction, alternatively with radiation therapy. And then if it's too late and the cancer has metastasis over your body, then you need to go and do chemotherapy. Typically, about half of the cases of cancer will undergo some radiation therapy at some point. So during this talk, I will focus really on radiation therapy, although we have worked a lot on the chemotherapy and a bit on surgery as well. All right. So radiation therapy also, it looks like it's very space-age technology. It dates to the 60s, where you had this very first machine which treated people with a radiation source, which was physical, and then you would control how the rays would hit the patient. Nowadays, you have what's called LINAC, linear accelerator, which creates the radiation on demand. Right? So there's not a radiation source in the machine. It just creates that when you want to treat the machine, and those machines are much more modern, but of course they break more, and then you have a lot of issues around that as well. As a comparison in radiation therapy the difference between radiation therapy and chemotherapy is basically that, of course, the doctor is a bit different, but rather than having pharmacists that inject you, that prescribe drug, and then the nurses gives that to you, then you have physicists who control the machine, the radiation stuff, and then the therapist will operate the equipment. There's a flow before you are able to get treated, which consists of the referral, and then having an appointment with the doctor. And then if they decide that you're going to go radiation therapy, you will get through simulation, planning, treatment, and then follow-up. So I'll go into these with more detail, but these are quite detailed workflows, right? This is the actual workflow from a regional hospital that doesn't do research, they just do traditional stuff. So there's really a lot of details about what's going on before you can treat it. I would speculate that radiation therapy is probably the line of medicine where actually the most stuff happens where the patient is not at the hospital. Right? The amount of preparation and involvement of the staff to prepare for you to start your treatment is huge as compared to other things where typically when the patient's there, a lot is happening, but when the patient is home, not much is going on. All right. So just to recap, the way it goes is the patient first comes to the center, and he goes a scan. So they will mark the patient with ink, or sometimes they will tattoo them. And then the room has a set of lasers, so the patient is perfectly aligned. And then he goes to a very detailed CT scan, and we create a 3D model of the body of the patient. From this, the doctor will indicate where are the tumors, where are the organs, and then a very sophisticated piece of software will actually compute how the radiation should enter the body and actually hit the tumor, but not the organs that are around that. So this is very, very sophisticated software. It costs typically millions to hospital. It runs on like farms of GPUs. Yes, it's basically this solves, like the software saves your lives, right? After that, once the calculation is done, the doctor looks at it, and because the problem is very complex, and I'll say a bit more later on, the optimization does not really optimizes what the doctor wants. It optimizes some form of proxy of that, so there's a ping pong in between the doctor and the software through people which are called dosimeters. And then when that is done and everybody's happy, the patient comes back, sits on the table, they have aligned the laser on the mark, So make sure that he's exactly positioned where he's supposed to be. They run an X-ray. If the cancer is close to the bladder, they make sure the bladder is filled with the exact same size it was filled when you had this, and then they actually treat you. Typically, depending on the type of cancer that you have, you might come from 1 to 5 sessions to 30 or 40 times this, right? Typically, the more stronger the cancer, the less time you come, the heavier the dose. When you're just making sure everything is okay, you would come many, many times with very tiny dose every time. So how do we make this whole process more efficient? So I'm going to focus on 2 things. Essentially, the first one will be booking. How do we book these patients to make sure that we utilize those machines and facilities at their highest possible rate? And then in the second part, if I have time, I'll talk about treatment planning. How do you decide how the machine should treat the patient? And can you give the same quality of treatment in less time, right? Can you use the machine to deliver the same quality, but using less inefficient time? Okay, so that's kind of our spin is really around efficiency. So we're not trying to do better medicine or to do anything which is clinical. It's really about doing the same quality, but faster. Yeah.
I mean, the underlying assumption is that this is a scarce resource, right? I mean, there are not enough machines to treat everybody or enough doctors that are preparing everything.
Yes, that's a good point. So we assume that if we have more space or create more space, people would wait less. So you would be able to not really. I mean, everybody gets treated, but people would have reduced delays. Yes, of course, if the machines are half used, then that's not so interesting. But I mean, the second part, actually sitting less, and especially the very, very last piece of my talk, if I can get to it, the patient now spends an hour on the table, right? So if you can reduce that by half, that makes a really big difference in the life of the patient. Okay, so once you know that you should treat a patient, right? And all these things is going to happen, like the optimization and everything between that patient actually starts getting treated. When can you give them an appointment, right? So you know you're going to treat the patient, you know you need multiple days for the scans and everything, you need to book the scan, you need to get the doctors to contour, you need to have the dosimeters to run the software, they ping pong with the doctors until everybody, and then the patient can come. How do you know when you should start the patient? Knowing that your grid is most likely full, and the hospital we've been working with, they are really, really busy, so there's a lot of patients that are actually there. And most importantly, that you have really a set of different type of patients. So typically, you will have those P4s, or patients that had surgery before, and just to be sure that the surgeon didn't miss a tiny piece that could come back, you're going to give them radiation therapy. So typically you want to treat them in 28 days. It's not a big rush, not a very high danger here, but you don't want to have them waiting too long. These patients are typically those that don't get surgery, and you're really trying to reduce the tumor with radiation therapy. So you're going to heal them with radiation therapy. They might go surgery after, or they might need to have chemo after, but no, radiation therapy is a core component of their healing. So these are super important. So this is a prescribed by law, 28 days, and this is kind of a medical guidance. It's not really a legal thing. Palliative are unfortunately patients that are not going to make it, or statistically not going to make it, and are suffering heavily because the tumor is hitting their spinal cord or some part of nerve or anything, and so just giving them a huge blast fast is the only way to get the pain out. So you don't care too much about the quality, and there will be less safety controls on the mission that you're not hitting anything because they are suffering, so you want to alleviate that and you want to do that as fast as possible. There are also the categories that I'll ignore for the next 5 minutes, which is called P1, that you want to do ASAP, like right away. So these, in our first project, they were passing right away, but in the second project, we're handling those as well. Okay, there are different ways of doing that. You can think about stochastic optimization. I have scenarios, possible, let me come back here. I forgot something important. These guys, they are about 30% of your volume, and you know them day of, basically. They come in the morning, you have to do them tomorrow, or like something like that. So, and they're 30%, right? So you can't fill your schedule with these people. Otherwise, you can't treat those. And if you leave 30% open, then you are wasting possible resource, and you have these people maybe waiting too much before actually getting cured. Right, so you can think about stochastic optimization, building scenarios, maybe robust optimization. We didn't know that much well, that technique at the time. So that's a possibility. But typically in those cancer centers in North America, you book the patient in an online dynamic way. A patient comes, give an appointment, and so forth, right? So if you could wait a month and then book the next month, I think you could do it with this because you would have time. Now you're trying to produce the appointment when the patient is basically there. So you want to have something which is super fast. Some colleagues, especially in Ottawa and British Columbia, have worked on the Markov decision process because that's super fast, so you can train the model. It takes a huge amount of time to train, but when you have a patient, you can follow the Markov decision process and then give them an appointment. The problem here is that you assume, what's the name, regime, which is a constant, right? I forgot the name. It's I'm thinking in French, stationary regime, exactly, which is basically never the case because you have summer, machine breakdown, maintenance, a lot of things happen, so you're never in a stationary regime. But if you assume a stationary regime, then you could use something like that. It is very, very difficult to train by, though considering every little detail of the operations of the centers, however. There are online optimization techniques, so basically like ad placement, stuff like that are taking decisions in a fraction of a second. So these are very good because they are super fast, but they ignore a little bit the stochastic aspect of what you know, which is about to coming up. You have your trajectory, people who have surgery, you know they are coming, you know about, so you can incorporate that. So the way we did that 5 years ago, and I'm telling that just so you have an idea of the incumbent before I move to the more modern machine learning aspect, is using online stochastic common optimization, and thanking Pascal for the beautiful book on the topic, where basically you use a mix of optimization and simulation to, let's say, anticipate what's going to come, and then solve that with some form of algorithm, and then being ready to take a super fast decision when the time comes. So to do this, we combine two mathematical decomposition methods, which was Danzig-Wolf decomposition and Bender's decomposition, in the following way. Let's say that you can enumerate your patterns, right? So you have a patient which is coming. You expect that he's going to be ready in 7 days. And then you could treat them right away, let's say starting on day 8. So the patient would have waited 8 days. So you have a penalty of size 8. And that's your first pattern. But let's say that patient is a P3, so he needs to be treated by day 14. The only other place you could fit him is here. And then you would pay a penalty, let's say, of 50 per days, which are overdue. So that pattern is much more extensive, right? So you can enumerate all the patterns on all the machine. And then you have a Danzig-Wolf formulation. In this context, it was not so hard because all the appointment times were the same. So you can do a lot of simplification. That will no longer hold a bit later on. This also, we assume that time that was fixed. We have other papers where we work with that using constraint programming and other technique, but I'll skip that for today.
Sorry,
yes.
Please repeat what the 2 times 50 was there for? Is it
because you're 2 days late, right? So you're starting on day 16. So 16, these are waiting times, and these are late times. So I'm more or less going to always assume two kind of weighted objective functions of waiting time and overdue time. So the set formulation looked like that, and the way we figure out like the form of a consensus or stuff that Pascal was proposing in his book is we looked at the dual value of that constraint, which was a capacity constraint. And if you solve your column generation approach and you have enough scenarios that you handle in a kind of L-shaped matter, and then you could do a bunch of small tricks to make that run reasonably fast, then the dual value of that constraint gives you some kind of the marginal cost of booking one more patient there. And on some sense, you have the existing, like the XR, the existing is the patient that you're trying to book, and that assumes for existing patient, and then the Ys are basically simulated patient under scenario omega. And then if you generate enough of them, you kind of anticipate the future. But once you solve that, you can just pick the spot that has the lowest reduced cost and book the patient there. And so we did that. And we tested that on a regional hospital 5 years ago that was just opening. And they were they were open for, let's say, 6 months or something like that. So they had only 2 machines. 400 days, so 4 months, almost 180 patients. And so that is what they were doing, some kind of first come, first serve with a delay for the 28 days. So they would basically cheat in saying if a patient is a P4, let him wait for 14 days and then treat him as a 14 days and then do first come, first serve, right? And you see that actually they had a lot of these guys were super late, but all of these guys were on time. And then we were able to reduce that significantly. And then the way they would handle these guys in the end, they were just doing overtime to kind of get them treated. Just get that. Okay, so this although this is not really recent, I wanted to go you through to see that this is the incumbent. Like typically, nothing else has been really proposed since that was able to solve this kind of problem in a fraction of a second, handling all the detailed constraints, all the machine, everything. So then let's fast forward about 5 years. In 2020, during the pandemic, we talked with the university hospital. And then they are way larger, 10 linacs of different brands, different types of categories, thousands of patients, tens of thousands of appointments. Appointments vary from 25 to 50 minutes, so all the assumptions about not figuring out the day, everything, nothing holds anymore. And you need to be able to schedule these people as they come. So we had a couple of projects. We worked at that with a student that came from the Netherlands, actually, and they were... Yes, no. Yes, but no. So that was so there were two students actually. The story we had two students at the center at the same time, and one was which was not Toussaint Pham and Patrick, came from I think 20, and they were saying that in the Netherlands they would solve for 1 week ahead of time. So we work on a deterministic model that would solve the problem, knowing everything. And with that project, we did a bit of the same, but we wondered whether that could be used after. Like if we have the deterministic solution, can we use that to make dynamic decision real time? So this is what we did here. Again, a bit of statistics on the problem. You see like these are the palliative patient, P1 and P2. They're about 30% again of the volume. And you see that this hospital is crumbling under volume, right? Like everybody's late. So like 75% of the patients are treated late. I mean, I have to thank them. They let us publish that. I thought they would just ban us for putting that out there, but they say, yeah, that's reality, so it's fine. So I'm allowed to tell them that how bad they were, but that's fine. And so the objective was trying to make that better, and especially I think they were really caring about those guys here, like these people that are suffering, 80% are not treated and waiting while they're in pain. So minimize overdue and waiting time, same as before. So this is the way that they were doing it. Typically, it's a greedy algorithm. So you say, I have this patient here. He has a 3 fraction. Okay, so that's atypical for P4, I should say. Maybe it's a P1 then. And he needs 50 minutes, right? This 5 minutes time slot, 50 minutes. And so this is my days. I assume, let's say that I need 10 days to be ready, to be able to treat them because of this type of plans and everything. So now this is the amount of slots that are remaining on those days, right? So the first day that I can schedule that guy is here. So if I do that, then I log these things, and then I have only 1 slot here. So that slot is left, right? Because there's no such thing as a 5-minute treatment. So I mean, that's worse, but you're kind of wasting capacity if you're thinking this. So, and this is because you're a bit myopic. So you can think, okay, I can do a bit before. I could wait, right? So let me wait a couple of days, let's say a week, and at the end of the week, everything which is not urgent, like the curative patients which are not suffering, I will schedule them at that point. And then I will look in a week and then schedule them at that point. So that's closer to the European model, where you schedule once per week for the following week. But the palliative patient, then I will do them on arrival, right? If the patient's urgent, I'm finding a spot for him. If it's not urgent, I'm delaying until the end of the week, so I have enough people so I can do a schedule. And we played around, as you will see, with many variants of how much you should wait. Now, an interesting aspect is that we try, let's say I know everything, right? Let's say I have all the information for the coming months. I know all the patient, I'm trying to build an offline solution, just trying to see how good am I. So here I know all the future, everything's unreal. I build a large model, which is very, very hard to solve. And I do that, I solve that over a long time horizon. So to do this, in theory, having all the details, you need to have some form of branch and check with logical constant programming for handling all the specificities of the intraday scheduling, and then something else for the long term. But I'm going to ignore for this talk the aspect of the intraday scheduling because I don't have time to give you all the details. So I'll just give you the math for the scheduling the days of the problem. So for the objective, we used, again, weighting and overdue, which is basically the same. We use a log function, which kind of is counterintuitive because you would think like the more you weight, the more you want to have a penalty, so we should use quadratic. The problem is that there's so many patients that quadratic explodes, like the numerical value of the objective becomes very, very large, and then you lose things, like 1 or 2 patients, they are 1 or 2 late because that falls in the gap. And you don't want to do that. You want to have the patients that are almost on time, you want to have them on time. And it turns out that when you know everything, not that many patients are super, super late, so that there's not this long tail of people that will be very, very. And this kind of an idea of weight decay in machine learning as well. Like people who are close to 0, you really want to push them to 0 because they for the government, they count on being on time. So the log function produce that and also allow to keep the numerical value of the objective under control. Then it's basically simple stuff at that point: assignment, patients ready, capacity of the machine, preserving some capacity, making sure that you force the system to preserve a lot of space for those P1s. Okay. Like I said, we ignore the intraday scheduling for a matter of time here. Okay, so now the question would be, when should I start? And that's why I want to have some let's say, prediction-based model. Let's say, oh, I bet you should start here, on day here, right? Because then you're avoiding this waste here. But how do you know, and how do you produce this prediction, and how do you train a machine learning model to do this prediction in a fraction of a second, knowing that this is based on the scheduling that's quite heavy to manage. So this is the pipeline that we built. So I think this is the 3rd time I present this, but it's the first time that actually I'm going to go really into the details of the fundamental, and I'm happy to pause here for 5 minutes and discuss this with you if you have insights about what is it that's happening, because I think this is one of the value of this type of workshop. So let me walk you through it. So you generate instances, right? So we have a bunch of distributions, so we fit a distribution on historical data, and now we can generate bunches of patients based on reality. We run the offline scheduling module, so we produce an exact schedule for say, a few months that would have been the optimal schedule, knowing everything. Okay, so that's our optimal offline solution. Now, this is the interesting part. We generate training data, right? And we're going to use features from the patient, the present, labels that we're going to be obtained from the offline solution. So the next 2 slides, I'm going to dig into this. Once that's done, we have the regression model, and then we train that to, we use the trained regression model in practice to schedule the patient, and we have a simulator that basically re-simulates many possible stuff. Yes?
So it's regression, so it's a continuous time that you predict, or is it more an action, like which of the coming 1,000 time slots should the story?
No, you predict the delay. So for example, if we say we need 10 days to be ready, we predict, should you wait 1 day more, 2 days more, 3 days more, and so forth. So it's a regression based on number of days. And I think we round them. Probably if it says 3.5 days, I think if I'm correct, we would round them up. Yeah. Okay, so this is how we create the data. And I think this is the most interesting part of this project. You have a set of patients, the capacity of the Linux. Like this is given by your optimal solution, right? You have the fraction length. This is part of the data of the patient, and so forth. So whenever you create a snapshot, right, they call it a data point, but it's really like a snapshot from history. You have this. So phi is the the moment in time that you're looking at, right? And so that will be the used, or the capacity usage at that time with the assignment that you've done until that time. Okay, and then all of this are the characteristics of the new patient that you're trying to book, right? It's treatment time, its due date, the number of fraction that he requires, and R is not there. Okay, anyway.
One question. So you're learning to predict the waiting time under the current algorithm, which is this optimum solutions. So there's nothing inherent about that this is their inherent waiting time. It's a function of the algorithm that you're going to use for
Yes, because any patient could wait 0 if I decide to prioritize him over the others.
So you're going to learn to predict what your algorithm would do with those patients from this training data. Or what at least the offline algorithm would have done.
Exactly. So this is what I'm hoping that we have a discussion about, because I think it's nice, but I think it also has a little bit of flaws. So in a sense, so this is my X and my Y is typically this W star. How much did that patient wait in that optimal solution of the offline patient? And I'm trying to estimate that, and I have a loss function, which is basically standard loss function from any ML algorithm. I think we use a mean square error or something like that. So a way to think about that is MIP as a labeling machine, right? So I have all of this data. I mean, if I look at my data, it's a set of patients for 4 months. I don't have labels. Now I create a bunch of sets of labels using a MIP. So that's a way of thinking about it. So how do I know what's good? I ask the MIP, give me a good solution. It gives me one solution for this patient. That's considered ground truth. But is it? Another aspect is to think about the same thing, but say, so this is a form of state, right? So this is the state of the system at some time. So I had this remaining capacity, and then I had this incoming request. And then I'm going to take this action. I'm going to decide that this patient waits this much. So it's a limited action. Basically, you have like plus 1 day, plus 2 days. You have 20 possible actions. Okay, so then the optimal solution, right, is a set of decisions over these. So the optimal solution is a trajectory or an episode, right? So is there MIP as an episode builder, right? So I have a bunch of stuff, and MIP is going to create a long episode of everything. And then I'm going to now rework that and train my regressor based basically on the stuff. So there is some link here with not really reinforcement learning as a training model, because it's not at all trained as a reinforcement learning algorithm, but you do have this sequence of decisions that are chained for creating the optimal value, right? This is only true because that was part of a long sequence. So this is what I think is an interesting, will be an interesting focus for us for the coming months, is trying to understand really how to position this as a frame, not really as a framework, but let's say as a question, right? If you build your label with MIPS. I'm going to talk about that a bit later, but let's look at the results. To generate the data, we use a Poisson distribution that's fitted on the, well, at the moment we use a Poisson distribution that's where the parameters are estimated based on the historical data. Same thing for the treatment plans. We use an empirical distribution of what they've been doing. And then we played, in the paper, we play a lot with number of linacs going from 4 to 12, I think, and then we have variable arrival rate based on the configuration. So we go from, let's say, the minimum size cancer treatment center to the large scale, the largest Canadian size hospital, I think. And then we generate 500 instances. We solve those 500 instances with a MIP, and then we train based on those 400, and we keep the rest for testing. So here we didn't use any deep neural net or something like that. We just used basic machine learning algorithms, and it turned out that gradient boosting worked well, so we kept that. And that's what I say is kind of a simple regression. But the like coming up with the label costs a lot, but solving the regression is easy. So this is the, let's say, the dynamic aspect of things. An offline is you know everything. The greedy, basically, you can dispatch. The greedy you can dispatch at admission based on like the first available slot, or you could use the prediction-based algorithm. And then we have all the batching. We basically wait until the end of the day and schedule at that point using a MIP. I wait until the end of the day, the week, and schedule everything using a MIP. And then daily greedy is wait until the end of the day and then just sort the patient and then schedule them greedily. Like this is typically what they would do. So they would do either this one or some hospital we see wait until the end of the day so they know who's urgent, and then they prioritize the person that's urgent, and then they move on to the next. It is something that was also asked by the referee, so we did that. So I'm going to just show, yes?
So, and how do you use the predictions?
So when a patient comes, you know the state of the system, you know the information of the system. So that's basically, this is your feature set. So you just put it in the regressor, and it tells you wait 3 days extra. So you know you have your basic 10 days plus 3, so you schedule them at the...
And you insert that patient immediately.
Yes. And if there's full, then you delay by 1 more day. So it's possible that it's not feasible, but here is just a delay, so you can always delay by 1 more day or 2 more days or stuff like that. So in the paper, we have a lot of these tables, but I'm going to show just one. So what you see here, on the left side is just waiting, and here it's overdue, so it is highly correlated. On the leftmost one here is offline, right? Perfect information, that's the optimal solution. Everything in between is the greedy and then the batch. And then on the rightmost one, you have the prediction base. So you see that prediction base actually comes quite close to offline. In terms of it will delay. So you see here the P4s are a little bit more delayed, even more than offline and more than the batching. But you are able to create the space for the really urgent one, right? And even the overdue are really reduced. And it's smart in the sense that it does understand that these guys can be delayed more than those guys, which all the batch and even the weekly batch that had the MIP with the same parameters, right? The wait function we use for the offline data is the same function we use for the batching MIP that does every week, right? It's the same priority. But it seems that when you batch, you're not really able to discriminate, right? If you look like here, the P3s and the P4, they are not, like these guys are getting more delayed, which is reversed. Like you would see these things should be below, right? They're higher. So it seems that the batching system doesn't prioritize enough these over there, and they're clogging up the schedule, so you have no. So remember that these guys, I always insert them right on, right? So I'm only asking the prediction what to do with the non-urgent one. The urgent one gets the fastest, the first open slot. So it's all about creating space so that the ASAP scheduling has room to schedule these people here. All right. Then we replay the year of the actual real patient. Okay, so now I don't have an exact Poisson process, so this is the actual arrival. So we use the, I think it was an exponential smoothing or maybe a mobile average or something like that, to come up about a 10.1 patient per day arrival rate. And we use their configuration. We use their 7 mainstream Linacs that are treating the same amount of patients, using their number of hours and everything. And when you look at the results, you see that we are actually really reducing the waiting days, right? We're coming close to the objective for the urgent patient, but we can't do magic for the... So we're delaying a little bit the non-urgent one, but we're really cutting down the waiting of the urgent patient. So that seemed to be quite interesting. Now, what still needs to be done here is to do, using this technique, using the actual intraday scheduling, which plays a role, because not everything is feasible when you come to intraday. But the main driver is if you have capacity on one day for one patient, you should treat them that way, right? And then the intraday scheduling is really about nice-to-have features for the patient, the time that he wants, the flow on the machine and everything. So nice thing about using SGBT is that you have explainability. You can use SHAP values for that you can generate quite easily, and then you know like why you are delaying this patient, right? Okay, because he has a long number of fractions, his due date, whatever. You have the explanation, and then the people in the hospital really thought that would make that more acceptable eventually. Okay, so I'll wrap up by having a little bit more philosophical question about that pipeline. So when you're training the regressor, you're using your offline solution, and then your regression engine thinks that labels are ground truth, right? That's the way that these things are built. So it tries to reproduce that decision. You're saying like, this decision is the optimal one. But we all know that there are often many optimal solutions, right? On the other side, the optimization when doing the offline solution, it assumes perfect online information, right? It doesn't know, the MIP doesn't know that this is an uncertain process, that things are going to come, that they might be differently in everything. And so the question is that should we using stochastic optimization here instead of deterministic optimization? But it's already a humongous amount of time to train all of that because you have to solve hundreds and hundreds of MIPS, which takes hours sometimes to solve because they're really large scale. So how do you build a solution base that's aware of the uncertainty? But even stochastic optimization, right? We're not going to execute any of this solution. We're going to use this solution to train a MIP. So maybe we need like the reverse of what we've been saying all week. We were talking about optimization, aware, cognizant, or focus for learning. But now maybe here what we need actually is the reverse. We need some optimization engine that's aware that is actually building a training set. And so what are the great or the important property you need in the solutions so that the training is going to be, you need probably diversity, you need stuff like that. So you're building a data set with your MIP engine here. And yeah, so that's what I'm really curious about at the moment. So if you have some thoughts on this, I'm happy to hear them, or we can just ping me at the coffee break or later on. I will be super enthusiastic to discuss that. So I can pause for, how much I'm good, for a couple, 1 minute or questions, otherwise I'll move to the treatment planning. Yes.
Is the uniqueness of the optimal solution when you label an issue, because you probably have many optimal solutions.
Yes.
So then the label is ambiguous in some sense, because if there are multiple equivalent solutions, you could have stumbled on any one of them.
Yes.
And then that would have affected the model.
Yes, that's a very important question. I don't know. One of the things that struck me this week is trying to talking with yes, so maybe contrastive learning here can be something interesting. Like if you play with this symmetries in the optimal solution, you can create solutions. Say all of these are basically similar, right? This patient waited more, this patient waited less. I don't care. Like what is really important is whenever some decision made the urgent patient wait more, for example, or something like that. Yes. And how you generate, I mean, this would allow, for example, to solve much less optimization problem, to build a bigger data set, maybe increasing the quality of the prediction and accelerating the treatment time, the training time, yeah. Mm-hmm. Yes?
To me, it feels very much like you're doing offline RL.
Offline?
Offline reinforcement learning.
That's what I was thinking yesterday when I did this episode stuff, but I don't know this literature or if it exists or.
So it's not really regression, but I understand it's not classification. It's ordinal regression basically. So you want day 1 or day 2 or day 3, and you formulate it as a regression because you want some smoothness, probably on the action space, rather than saying it has to be day 3.
But it doesn't have to be day 3. It's true. Yeah, you need to delay, and you're trying to create, but it has to be based on the context, right? It's really based on the state. Like the delay that you put is based on the current state of the machine, right? Because if it happens that what is difficult about these things, right, is this patient, they come for 30 days or 40 days. So if you have, let's say, a little hump in demand, right? If you have a hump in demand in energy or retail, 2 days after, it doesn't show anymore. If you have a hump in demand here, and you have a bunch of P4 with 40 fractions that come because one new doctor got hired and he specializes in prostate cancer, and then he has all the influx from the regional hospital, he just clogs up your machine for 2 months. And then you have no more room because these people will come day after day after day for 2 months. And so you need to realize that live when you have new patient, that the region where you are now is very, very different from where you are, and it's not going to change for a couple of weeks. So it's true that trajectory is super important. So I think the trajectory and the state and the action are core to this, but it's not trained based on individual reward. Like you don't have a reward until you're really at the end. Because, for example, if I book this patient, I know how much time he has waited, but maybe it takes 40 fractions, so it's going to delay 10, 20 urgent patients that are going to come after that. And then the negative reward of those decisions should be incurred to that particular patient and not to those there, right? So the reward is not really based on the action itself, it's like delayed reward in some sense, right? Yeah. Okay. And let me jump to the second part. So I have, 20 minutes, 15 minutes? 10. Okay. Okay, let's talk about treatment planning. So you have these machines. they shoot radiation, and the way that you can make sure radiation hits the tumor is you can control the aperture or the shape of this thing with tungsten leaves. So you move these leaves, and they block the rays. And then you typically, in the old days, you would stop at a certain amount of angles around the patient. And then with playing with the shape, you would shoot a couple of beams. So that was called intensity modulated radiation therapy, or somebody called that rather step and shoot, right? You move to a place, let's say I move here, I shoot a couple of things by playing with the aperture. I move here, I shoot a couple of rays playing with the aperture, and so on. That would take time, and it would burn like the skin at these places, so you would have like hot spot here. And the tumor is good, but the tissues, they are not really protected. And this is very cold because nothing came here. They came later on. I mean, the machine for decades were able to do what's called volumetric arc therapy, which basically moving while shooting, right? So the machine moves, single round around the patient, tungsten leaves move at the same time, everything's moving. It took 10 years to do the algorithms that could support that, because everything's moving. The amount of degree of freedom is humongous, but it gives you a much better distribution of those around the patient. So now everything is, you don't have these light blue things which are hotter, closer to the surface. They're much more deep in the patient. For example, here, this is bones, right? So this bone, they would get radiated, and that's not very good. Okay, vocabulary. A voxel is a cube inside your body. A sector is an angle of the machine around you. An aperture is the shape of the tungsten machine. A beamlet is a single beam, right? We can think like it's the minimum amount of radiation you can study. A single beam which starts from a position on the machine, goes through you. And the dose is the amount of radiation that's left in your body by this beam. Okay, and your decision is you're trying to figure out the set of aperture for every 2-degree position around the body. So once you have that, you have your continuous movement, right? So you need to control the leaf and the intensity of the machine. And you're trying to get the best plan as possible. So you want that the dose that the tumor gets is, looks close to what the doctor says, as well as it's called the organ at risk that are around that. And what we added in this project is try to control treatment time. And to do so, we need to solve this with column generation, because the problem is it becomes extremely big, right? If you take this toy machine, which is 5 by 10, so I have like 10 tungsten beams that can take 5 positions, okay, and 100 sectors around the patient. This is the number of aperture that you would need to have for a single position, right? But the real machine is 80 by 80 by 180, so it's even bigger than that. No, I don't even know exactly how that computed that, but it's just, yeah, it blows up. But everything blows up in commercial optimization, so that is why it is so much fun. But here the thing is that everything moves. So we did that with column generation because the only way people were doing that before is they were saying, okay, I want to have this aperture here. They would optimize that. And then they would say, do me this one, and then do me this one. But if here and here, the aperture are completely separated, right? One is fully open, and this one is closed, and this one is fully open. Then you have to move those leaves up, and they are slow. So then the machine will go very slow because the leaves keep on moving a lot like that. And it's not very good for the maintenance and so forth. And then when you need to change those, the machine is down for a couple of hours or days. So we basically were building trajectories, complete trajectories with column generation. So so the objective is a quadratic column generation because you're minimizing dose deviation. You have delivery time, and then a bunch of constraints that come from the mechanical aspects of the machine, like movements and stuff like that. So the math is a bit like that. The interesting part here is the fact that this is quadratic, so you can't solve that directly with Cplex because you play with speed intensity is not convex, so we had to play around with that to make that solve, but I will skip that. What I want to say is that the problem is, I'll skip this as well. The problem is huge. So what we came out to do is actually, and this is where the machine learning was interesting, is that we said, okay, but some of these voxels, they must be the same, right? So you can have 2 voxels that are very close. Like, do we really, really need to have like a constraint saying like, this voxel gets this much, and the voxel just by it gets this much, and so forth. But it seems that you can't really use the organ itself as a clustering algorithm because it really depends if a bone is projecting some shadow on some of these. And another one, even though they are in the same structure, they might be very different from the amount of radiation that they get. So what we did is we we decided to downscale the problem, and they were selling less. People from Massachusetts General Hospital, yeah, just throw away 90% of your voxel, just randomly sample, you'll be fine. But it doesn't work. So what we did is we downsized the problem using unsupervised clustering. So we basically built a huge feature set that was the amount of radiation that the voxel gets from everything. We suppose all the apertures open, all the beamlets shoot, and we look like every possible beamlet is an entry in your feature matrix, right? So this is a huge feature set. So we use something very simple, k-means, and we just say now downsize this to 5% of the, like if it's an organ which is safe, it's probably not going to get a lot of radiation, so let's divide by 20. And if it's a tumor, then we need more precision at the edge, so we reduce it by 6 to 10. And it runs super fast, and for some reasons the clustering goes down after a few iterations, and even 1 second you have reduced everything. Now the question is does that impact? I'll skip the thing. Does that impact the quality? Not much. Okay, so these are, if you like multi-criteria optimization, this is multi-dimensional, multi-criteria optimization, because every curve is an organ, and every point in here is the fraction is a fraction of an organ getting at least some dose. And so what the doctor wants, to conclude on that remark I had at the beginning, what the doctor wants is some form of conditional value at risk constraint saying 95% of the tumor should get more than something. So you want to have those tumor curves. You want to go all the way to 95, 50 rays, right? So you want to get them basically to not fall before they hit 25 at the prescribed dose. If I want to get 60 grays to my tumor, the point here should be at 95, 60. And then after that, I want it to drop as fast as I can for these two. All the rest, they should be as bottomless as possible, getting less than radiation. And you would have something, for example, 30% of the rectum should get less than, say, 50 gray or something like that. And you want to be below this point. But we have another paper on how you do these conditional value at risk within column generation, but yes, no time. Okay, so we basically cut the solution time by a factor of 6 using this downscaling. And using this trick, we were able to cut the delivery time of the treatment by almost half for the same quality. And there are differences, but they don't matter. The constraints are these are the tumor, they are very, very close. These things, they are way below their medical threshold, so that's fine. I don't know if I have 2 more minutes. Then we looked at robotic surgery. So now the robot moves around you, and the robot, there's a bunch of nodes. There are hundreds of nodes. They are positioned around the patient, where the robot actually has a very, very tiny beam that goes through your body. So that's why it's called cyber knife. It's like a knife. It really cuts a small piece. And this is much, much more precise than the big machine, but much slower. So they typically use this for lung cancer because you can hit metastasis in the lung, and the robot can follow your breathing evenly. So they put a piece on you, and the robot knows how you breathe, so it follows that. It's extremely precise, but super slow. It takes 45 minutes to an hour to deliver a treatment. And 70% of the time is the robot moving without shooting. So the robot moves, shoot, move, shoot. But you have to decide, right, out of these hundreds of places, which one are you going to shoot from? And then, because it gives you different angle, right? So there's a trade-off there. There's not a single possible solution, but you have to move around these things. So what we want to do, reduce time, so minimize the distance covered by the arm, maximize the treatment quality, fit as most as possible what's prescribed. And then there is something, you don't want to shoot from 2 nodes that are super close to one another, because more likely, the skin at that point, entry point, will be close to one another, and you don't want that. You want to shoot from angles that are as spread as possible. So we trained a reinforcement learning agent to do that, because it's close to TSP. Xavier is here, yeah. We've been playing around with this in the past, so we say, oh, this looks like TSP. You're trying to moving around the nodes, except you don't know exactly about reward. So action space is where do you go to? Reward is basically, if it's, we're using basically a ratio, right? So when you get to a node, we look at what is the dose that you can give, the ratio of the dose you can give to an organ at risk, divided by the dose that you give to a tumor. And we want this to be minimal, right? You want to have something which is as close to 0 as possible, which means that you're not hitting anything important. And at that point, you can really blast because you're only getting the tumor. And you get that by running a Monte Carlo simulation engine. And then when you arrive at the last node, the last terminal node, then you can evaluate the spread of the nodes, and you get a reward for having a set of positions that are as spread as possible around the sphere, which encompasses the patient. So I'm going a bit fast because I have no more time, but that's the general idea. We use a basic traditional pipeline for RL, so I'm not going to play around too much with that. I'm going to look at the result. So we tested two things. So our approach, DQN, we also ran the model on Gurobi. We computed all the doses for all the nodes, and then we just say build a TSP. It times out at an hour, but you do have a feasible solution, so you can compare against that. And so the objective is the quality. So you see that Gurobi gets really the best quality. And then we have heuristic, like nearest neighbor, or do something random, just to make sure we're learning. Execution time, yes, and also machine learning is 1 second, and Gurobi is an hour. And this is the time it takes to deliver the plan. So all these methods, they are super fast, right? In terms of they can treat the patient in half an hour instead of an hour. Gurobi and DQN have pretty good conformance to plan quality. Everything which is random is awful. And clinical tests, we couldn't really recompute this, but the doctor said that our clinical quality of these things were acceptable for treatment plans. So they have something which is more or less the same quality, but they take an hour to deliver that to the patient.
And what's the quality of solutions that Gurobi can give you in 3 seconds? Because, it's taking a long time to prove optimality of findings.
It's a good point. My feeling, my souvenir is that it took a while just to get started and get something. But I can dig it out. It's a good question. Yes, so I'll finish with that. Long waiting times it's not only a question of efficiency, it's a question of anxiety for the patients while they're waiting to have their appointments. Getting the appointment canceled and everything is always a big stress for everybody. So it's important as well from that perspective. And these are not real people, they were generated by DALI. So I tried to get all my pictures generated by DALI, but I completely failed. I spent 10 minutes trying to get what I wanted, so in the end I didn't use that, except for those people that were